Single context reading just totally fails. So when a machine tries to read a sentence strictly word by word, straight from left to right, it immediately hits a brick wall. Think about a sentence like, the bank raised its interest rates because inflation was increasing. As humans, our brains are just amazing, right? We instantly link the word bank to money and we seamlessly connect it to interest rates. We do this without even trying. But an AI model, it struggles to see those connections linearly. To the machine, it's just a string of isolated individual tokens. And listen, it's not just one type of connection the AI is missing out on. To truly grasp a sentence, a model has to track grammatical relationships, semantic meaning, and distant word connections all at the exact same time. A basic single attention mechanism is going to completely fail here because it just cannot simultaneously juggle all those distinct layers. It's kind of like trying to listen to 3 different intense conversations at a loud dinner party using only one ear. You're going to miss things. This massive bottleneck is exactly why we need multi-head attention. Moving to section 2. A quick self-attention basics refresher. Specifically, we're talking about the query, key, and value. So before we bring in a whole team of attention heads, let's just look at how one works. It all kicks off with a query vector, or Q. Think of the query as the model asking, what am I actively looking for? For instance, imagine the sentence, the student opened the laptop because it was slow. When the model processes the word it, the query vector is essentially the model trying to figure out what it is searching for. Is it the student, or is it the laptop? Well, to answer that, the query has to check the key vectors, or K. The key represents the idea of what information do I contain. Every single token in the sentence holds a key. Think of it like a brightly colored label on a file folder. It acts as a matching point for our query. The model compares the query to all the keys to see which ones are the best, most relevant matches. And finally, we have the value vector, or V. This answers the question, what information should I actually provide if I'm a match? Once the model compares the query and the keys, it generates these attention scores. It then uses those exact scores to create a weighted combination, basically mixing together the most relevant information from the values. That perfectly mixed result is the output of self-attention. It represents exactly what the model has decided it needs to focus on. Section 3. Inside multi-head attention. This is the core mechanism of the whole thing. Now, here is where we take that basic query key value concept and completely supercharge it. Instead of relying on one single mechanism to understand everything, imagine deploying a whole team of specialized expert analysts, and they are all looking at the exact same input at the very same time. Let's use a simple phrase, AI understands language. Instead of creating just one set of vectors for these words, the model projects these token embeddings into multiple independent heads, say head 1, 2, 3, and 4. Every single one of these heads gets its own unique learnable transformation matrices to create its very own Q, K, and V. Now, what's really fascinating here is the specific mathematical sequence happening inside each head. First, it creates those learned Q, K, and V transformations we just talked about. Second, it calculates the similarity between the query and the keys using a dot product. Third, and honestly, this is just a genius engineering trick, it divides that result by the square root of the key dimension. Why bother doing that? Well, as vector dimensions get huge, dot product math can actually explode out of control. Dividing by the square root keeps everything perfectly stable. Fourth, it applies a Softmax function to turn those stable scores into precise attention weights. And finally, it multiplies those weights with the value vectors. So, with all these independent attention heads calculating away in parallel, we eventually need to bring it all back together for a unified understanding. So the model concatenates, or basically stitches together, all these separate outputs into one massive combined representation. Then it passes that merged data through a final learned linear transformation, which we call the output projection. This essentially takes all those parallel independent insights and tightly bundles them into our final multi-head attention output. And this perfectly illustrates why we absolutely need multiple heads in the first place. Take a sentence like, the engineer designed a model that predicts customer demand. We don't sit there and manually program the AI to understand the grammar here. Instead, during training, the network automatically learns these distinct patterns. Head 1 might independently learn to zero in on the relationship between engineer and designed. Head 2 might focus on model and predicts. Head 3 focuses on customer and demand. We're getting multiple, highly specialized perspectives from a single sentence, and it's happening completely automatically. It is honestly mind-blowing to see how the network just figures this out on its own. Section 4, the full transformer architecture, or how we go about stacking the layers. So, zoom out with me for a second. Where does this multi-head engine actually sit inside the broader architecture? Well, multi-head attention is really just one step in a much taller vertical stack. The data flows from input embeddings straight up into our multi-head attention block. Then it hits an add and normalize step, which, by the way, acts as a residual connection. After that, it passes through a feed-forward neural network and then hits another add and normalize step. And here's the kicker. This single structural block is then stacked repeatedly, over and over, building the massive, incredibly powerful foundation of the modern AI systems we see today. All right, Section 5, Power and Real-World Applications. So what does all this scaled dot product math and matrix concatenation actually achieve out in the wild? The impact is literally world-changing. This exact engine is the brain behind the large language models you probably used to draft an email this morning. It drives complex machine translation, allowing models to grasp deep grammatical nuances across entirely different languages. It powers text summarization and super advanced question answering. But hey, it's not just text. In computer vision, transformers use this exact same attention mechanism to map relationships between different tiny patches of an image. And in multimodal AI, it acts as the vital bridge connecting textual data with visual data. It does the whole shebang. But why is this specific architecture totally dominating the field? Well, there are three major strengths. First up, parallel processing. Unlike older recurrent neural networks, which, had to painfully read data sequentially, one bit at a time, transformer attention can process massive amounts of tokens simultaneously, in parallel. That's a huge speed boost. Second, as we just saw, those independent heads provide multiple, incredibly rich perspectives on the exact same data. And third, it flawlessly connects long-range relationships across massive sequences, making sure the broader context is never lost.
Finally, let's wrap up with Section 6, computational trade-offs and the future.
Look, as amazing as this is, there is a catch. The reality is, calculating every single token-to-token relationship across a really long sequence comes with a remarkably heavy computational cost. Actually, scratch that. It's not just heavy. As your token count grows, the memory requirements literally explode because the model has to check every single token against every other token. To fix this, modern AI engineers are evolving the architecture as we speak, developing highly efficient workarounds. Things like sparse attention, where the model only looks at a few crucial tokens instead of all of them, are designed to keep the performance high while bringing those massive compute costs way down. Grouped query and multi-query attention offer similar clever shortcuts to save on memory. So as we bring this explainer to a close, remember that a modern AI model isn't just looking at words one by one. Not at all. It is a massive, interwoven web of attention, dynamically calculating multiple mathematical perspectives at the exact same time, which leaves us with a pretty fascinating, provocative thought to ponder. If true machine understanding is fundamentally built on parallel, multi-head perspectives, as these models grow larger and more complex, how will their perception of context eventually differ from our own, very sequential, human way of thinking? Thanks for joining me on this deep dive today. Keep learning, and I'll catch you in the next explainer.